discuss part 1 of our module 3, Continental Drift and Plate Tectonics Theory. So at the end of this module, you will be able to describe the Continental Drift Theory, discuss the evidences that support the Continental Drift Theory, explain how the seafloor spreads, and explain how the movements of plates leads to the formation of faults, trenches, volcanoes, rift valleys, and mountain ranges. Continental Drift Theory. Geologic process continue to change the appearance of Earth. So how did Earth look before? So in the absence of maps, only archaeological finds may solve this puzzle. In 1596, Abraham Ortelius observed and presupposed that the shapes of the continents on both sides of the Atlantic Ocean seemed to connect each other. It was as if Africa was turned away from Asia and Europe. With the absence of valid measurements and proofs, the only speculation he could provide was that earthquake and flooding may have made a separation possible. So let's go back in the formation of the early Earth, a nebular hypothesis. So the Earth was formed about 4.6 billion years ago. It was formed by collision of particles in a large cloud of material. Slowly, gravity gathered together all these particles of dust and gas and formed larger clumps. These clumps continued to collide and gradually grow bigger and bigger, eventually forming the Earth. The Earth at this time was very different to how we know it today. Scientists predict that supercontinents will continue to appear. Today, the world's continents are slowly moving away from the mid-Atlantic ridge toward the middle of the Pacific Ocean. It is believed that they will eventually collide with one another in about 80 million years. So, in simplest definition, continental drift is the hypothesis that the Earth's continents have moved over geologic time relative to each other, thus appearing to have drifted across the ocean bed. The speculation that continents might have drifted was first put forward by Abraham Ortelius. In the year 1596, cartographer Abraham Ortelius noted that the coastlines of Africa and South America appeared to fit together, compelling him to propose that the continents had once been joined but were pulled apart by earthquakes and floods. In 1912, geophysicist Alfred Wegener developed the concept and hypothesized the continental drift theory. He claimed that Earth used to have only one supergiant landmass, where all continents came from. He called this massive landmass Pangaea. So, in the early 20th century, German scientist Alfred Wegener discovered the theory of the continental drift. He believed that the continents had been drifting across the Earth. Wegener noticed that Africa and South America looked like pieces of jigsaw puzzle. He believed all the continents were once connected into one supergiant continent called Pangaea. According to the hypothesis, Pangaea broke apart and each landmass drifted away from each other in different locations. Initially, two giant continents were formed: Laurasia, which comprised the northern continents in today's time, and Gondwana, which comprised the continents in the present hemisphere. The separation continued until the present-day continents were formed. In addition to this, Pangaea broke apart for the same reason that the plates are moving today. The movement is caused by the convection currents that rule over in the upper zone of the mantle. This movement in the mantle causes the plates to move slowly across the surface of the Earth. So about 200 million years ago, Pangaea broke into two new continents, Laurasia and Gondwana land. Laurasia was made of the present-day continents of North America Greenland, Europe, and Asia. Gondwanaland was made of the present-day continents of Antarctica, Australia, and South America. Wegener provided the following evidences to his continental drift theory. Similarities of fossils found in different continents. Many similar plant and animal fossils were found in the continents that are presently far from each other, such that it is unimaginable for an animal to have flown or swum to get to the other continents. For example, the fossils of Mesosaurus, a freshwater reptile, was found in Brazil and in Africa. Freshwater reptiles are not capable of swimming the distances between continents, unless the continents of Africa and South America were once together. Still another interesting find was Glossopteris, a fern plant which was found to have thrived in 5 different continents: Africa, India, Australia, South America, and Antarctica, that are presently separated by oceans and seas and are thus miles away from one another. So for this reason, the existence of Mesosaurus helps support the theory of continental drift. That is, the now well attested fact that South America and Africa were joined together into the giant continent Gondwana 300 million years ago, before the continental plates supporting them broke apart and drifted. On the other hand, Glossopteris fossils tells us the continents, especially Southern Africa, Australia, India, Antarctica, which are now separated by wide oceans, were once connected because the large seeds of this plant, Glossopteris, could not possibly travel a long journey by the wind or survive a rough ride through ocean waves. So we have a representation image of those organisms and plants that have interconnected with this supergiant continent Pangaea. So we have the Cygnognathus. This Cygnognathus is an extinct mammal-like reptile. The name literally means a dog chow. Cygnognathus was as large as a modern wolf and lived during the early to mid-Triassic period. It is found as fossils only in South Africa and South America. We have also an image of Lestrosaurus. So Lestrosaurus, which literally means shovel reptile, was dominant on land in the early Triassic, 250 million years ago. It is thought to have been herbivorous and grow to approximately 1 meter in length. With a stocky build like a pig, fossils of Lestrosaurus are only found in Antarctica, India, and South Africa. So there are many examples of fossils found in separate continents and nowhere else, suggesting continents were just once joined. Next evidence, we have presence of tillites in areas whose present climates do not suggest glacial formation. Tillites are glacial deposits from rock strata in areas that were once covered with snow. These deposits were found in South America, Africa, Madagascar, Arabia, India, Antarctica, and Australia. It is understandable if tillites are found in polar climates or areas where there is snow. However, for places that are presently known to be tropical and desert-like, such as Africa, Madagascar, and India, finding ice deposits would seem unreasonable, if not for the concept of drifting continents. So in addition to this, tillites, which are rock debris left by glaciers, as you can see in our image, indicate that the continents were once located in the South Pole. Tillites which are rock debris left by a meteorite, indicate the continents drifted apart when they were hit by a meteorite. Next, presence of coal seams in polar regions. Coal is a fossil fuel that originated from chemically altered remains of prehistoric vegetation. Usually, coal is found in tropical areas because the climate is warm and ideal for propagation of organisms. Because of this, there is a higher index of diversity and population in tropical regions. This is where organisms are mostly concentrated. Going back to the ancient fern glossopteris proliferated in certain areas of each continent. The shaded regions are the tracts believed to be where the organisms had wandered or spread. These places are the same areas where coal seams were found. Therefore, Wegener used to question why coal would be found in polar regions, such as North Pole and Antarctica, leading him to believe that these areas used to be near the equator and just drifted away from it. So in addition to this, there have been glacial deposits founded in tropics and coal founded in Antarctica. This supports the theory of the continental drift because coal originates from tropical plants, which can only be found in the tropics. Additionally, glacial deposits can only come from Antarctica, providing the theory. Next, continuity of rock layers found in different continents. Rock layers may be profiled to determine the history, age, and composition of materials in the environment. Part of the evidences of continental drift theory is the similarity of rock layers found in mountains that are on the opposite sides of the Atlantic Oceans. The Appalachian Mountains, the Caledonian Mountains of Scotland, the Scandis Mountains of Norway, and Atlas Mountains of Morocco were brought to be one mountain range in Pangaea. Later, the Atlantic widened and broke the mountain range into pieces. Next, similarity of rock types in different continents. The rock types found in Brazil, India, South Africa, and Antarctica seem to have similar layers and sequence. This is evidenced by a top layer, which is the youngest rock layer, characterized by lava flow, followed by a middle layer with fossils of Glossopteris, which was believed to have been extensive and widespread in the entire Pangaea, and a bottom layer of glacial tillites. The theory is that all these places were continuous and shared the same environment and history. In our image, it shows the rock layers. The similar layers of rock were formed in Antarctica, Australia, South America, Africa, and India before Pangaea broke apart, and Glossopteris fossils were found also in the rocks on each continent. So we have the plate tectonic theory. Wegener's theory initially did not gain acceptance from the scientific community because he could not explain why the continents moved. He just asserted that continents have been pulled apart by Earth's rotational force and some astronomical influences. Hence, his theory was given the little interest at the time. However, in 1940s, during an initial survey for ocean floor mapping and other geological explorations, certain findings lead to the discovery of more accurate evidences that would lead to the explanation of the moving continents, thus the birth of plate tectonic. As early as 1929, Arthur Holmes, a British geologist, suggested the idea of thermal convection. As Holmes put it, based on the fact that as a substance is heated, its density decreases and rises to the surface until it is cooled and then sinks again. The repeating process of heating and cooling may produce a current that is strong enough to make continents move. Holmes further suggests that thermal convection works like a conveyor belt. where the pressure that goes up could break apart a continent. The broken pieces that can be carried by the same currents to opposite direction. In the later years, the concept of thermal convection currents to specify that the heat is actually radiating from the mantle. So in addition to this, convection occurs when particles with a lot of heat energy in a liquid or gas move and takes place the particles with less heat and energy. Heat energy is transferred from hot places to cooler places by convection. Means that if this happens, continents will move. While the basis for the movement of continents progress, geologists started to use a more precise term to refer to the moving piece of crust as plate because it is believed that continents are not only once moving, as explained by Alfred Wegener. The boundaries of the tectonic plates were accidentally discovered and eventually studied during the magnetic surveys of the ocean floor and seismic studies for nuclear testing. So in addition to this, the thermal convection is referred to exist on a large scale in at least two regions of Earth, the liquid outer core with less heat particles and the upper mantle that behaves as solid for seismic wave propagation and as very viscous fluid for long duration and geologic processes including convection. The Earth's outer core is inferred to be mostly liquid iron. Convective flow within the outer core not only brings heat to the core mantle, where some of its heat transferred into the mantle, but also causes the Earth's magnetic field by motion of the electric conductive inner core material. As a background, the lithosphere refers to the crust and upper mantle of Earth. It is broken up into several tectonic plates that glide over the mantle. Tectonic plates are composed of oceanic lithosphere and a denser and thicker continental lithosphere. So the significance of tectonic plates in plate tectonics theory is the plate boundaries are important because they are often associated with earthquakes and volcanoes. When Earth tectonic plates grind past one another, enormous amounts of energy can be released in the form of earthquakes. After the plate boundaries were discovered, scientists were able to identify the 7 major plates: Pacific Plate, Eurasian, North American Plate, South American Plate, Indo-Australian Plate, Antarctic Plate, and African Plate, and several minor plates, one of which is the Philippine Plate. Plates movements occurs on types of boundaries. Plate movements occur on the boundaries. The direction of the movement depends on type of boundaries the plates have. Let us review the different types of boundaries briefly. First one, we have convergent collisions. Our boundaries where plates meet. They are driven by compressional forces. Two possible landforms can be created. One is trenches from the subduction, where a less dense plate sinks. So subducts means the plate will eventually sink under the other plate, while the other is mountain and volcanoes, where neither plate is subducted but instead is pushed upward or sideward. Convergent boundaries are where most of this destruction of crust takes place, specifically in the subduction zone. Okay, so in this case, it is relating to a compression plate tectonics. In geology, the term compression refers to a set of stress directed toward the center of a rock mass. Compressive stresses can also result in folding of rocks. Because of large magnitudes of lithospheric stress in tectonic plates, tectonic scale deformation is always subjected to the net compressive stress happens usually in the subduction zone. Subduction is a geological stress or the geological process that takes place at convergent boundaries of tectonic plates, where one plate moves under another and is forced to sink due to high gravitational potential energy into the mantle, where regions where this process occurs are known as subduction zone. The Earth's lithosphere, composed of the outer crust and the rigid uppermost section of the mantle, is divided into mobile segments called tectonic plates, in which the oceans and continents lie. Plates can diverge or slide past one another. Where they collide, they form tumulus convergent boundaries, where one plate is either destroyed, is the alternate term destructive plate boundaries, or jumps up against the other. Convergent boundary types includes oceanic-oceanic, oceanic-continental, and continental-continental. So we have the three types of convergent boundaries. The first one is the oceanic-oceanic convergent boundaries, where different oceanic plates run into each other. The older and therefore cooler and denser. One dives beneath the other, in other words, it subducts or sinks. Such as a convergent boundary includes a seafloor trench, marking the earthquake-rattled subduction zone, as well as an island arc, a line of volcanoes created by rock melt in the mantle associated with subduction. Other features of an oceanic-oceanic convergent boundary are the four-arc basin between the trench and the island arc, and the arc basin on the opposite side of the arc, as you can see in our image. So the features of subduction zone when an oceanic plate subducts beneath another oceanic plate are the same as a continent-ocean subduction zone. An ocean trench marks the location where the plate is pushed down into the mantle. In this case, the line of volcanoes that grows on the upper oceanic plate is an island arc. An example of oceanic-oceanic convergent boundary is that between the Pacific and Mariana plates, which includes the Mariana Islands arc and a subduction zone encompassing the Mariana Trench, the deepest part of the world's ocean. The world ocean is the name for the collective group of oceans on the planet. So in summary, if two plates that met the convergent plate boundary both are the oceanic crust, the older, denser plate will subduct beneath the less dense plate. The features of an ocean-ocean subduction zone are the same as those of an ocean-continent subduction zone, except that the volcanic arc will be a set of islands known as an island arc. The older plate subducts into a trench, resulting in earthquakes. Melting of mantle material creates volcanoes at the subduction zone, as you can see in our image. Next, we have oceanic continental convergent boundaries, where oceanic and continental plates collide. The former subducts beneath the latter. Because ocean crust, rich in iron and magnesium, is denser than the continental rock. Here again, a subduction zone occurs, as does a volcanic arc that develops on the continental side of the boundary. In between sediments slope against the continental margin form an accretionary wedge. So what happens at the oceanic continental convergent plate boundary? So in summary, when oceanic crust converge with continental crust, a denser oceanic plate plunge beneath the continental plate. This process called a subduction. Course of the oceanic trenches. The subducting plate causes melting in the mantle above the plate. The magma rises and erupts, creating volcanoes. The western coast of the Americas is part of the Pacific Ring of Fire, named for the Pacific Basin's energetic, volcanic, and seismic turmoil. Hosts this type of tectonic convergence along the Pacific Northwest coast. For example, oceanic plates subducting beneath the North American plate created the Cascade subduction zone, fueling the Cascade Range volcanoes. Subducting under the South American plate meanwhile uplifted the Andes and prefer the towering range with volcanoes. Both regions are vulnerable to severe earthquakes associated with these intense plate collisions. So we have also continental convergent boundaries. Convergent boundaries between continental plates are a bit different than oceanic and oceanic-continental mashups. Continental lithosphere is too buoyant to subduct deeply, so rather than a subduction zone in a trench, these boundaries encompass a thick mess of folded, piled-up crust. This compression results in massive mountain belts rather than the volcanic arcs powered by subduction zone magma in the other two cases. So, continental convergent boundaries is another type of convergent plate boundary. It's when two identical or two continental plate collides. Continental lithosphere is low in density and very thick. Continental lithosphere cannot subduct, so when two continental plates collide, they just smash together. The classic example of continental convergent boundary is the rump-fold overlap where the Indian plate drives into Eurasian plate. A tectonic collision that has thrown up the greatest mountains in the world, the Himalayas, as well as the vast high Tibetan Plateau. In the west, the Alps grow in similar fashion via the collision of African and Eurasian plates. So in addition to this, plates collide when two plates carrying continents. The continental crust buckles and rocks pile up, creating towering mountain ranges. The Himalayas mountain ranges were born when the Indian subcontinent smashed into Asia 45 million years ago. Next, we have the divergent boundaries. Divergent boundaries are where plates move away from each other. Plates move apart because of the magma that is being pushed upward in boundaries of the plate. When this happens, the slowly moving plates transport newly formed crust away from the ridge towards the direction where plates go. In plate tectonics, a divergent boundary or divergent plate boundary is a linear feature that exists between two tectonic plates that are moving away from each other. Divergent boundaries within continents initially produce rifts, which eventually become rift valleys. Okay, so a rift valley, as you can see in our image, is a linear shaped lowland between several islands of mountain ranges created by the action of geologic rift or fault. A rift valley is formed on a divergent plate boundary, a crustal extension spreading a part of the surface, which is subsequently further deepened by the forces of erosion. Next, we have transform boundaries. Transform boundaries are where plates slide past each other. Neither plate gets subdued. Plates slide past each other and the sudden movement can cause earthquakes. Transform fault usually happen in the fracture zone, in areas that connect spreading centers to the deep sea trenches in subduction zones. There are transform faults near Taiwan and Philippine Trench. So in addition to this, transform plate boundaries are locations where two plates slide past one another. The fracture zone that forms a transform plate boundary is known as a transform fault. A transform fault or transform boundary is a fault along a plate boundary where the motion is predominantly horizontal. It ends abruptly where it connects to another plate boundary, either another transform, a spreading ridge, or a subduction zone. Most transform faults are found in the ocean basin and connect offsets in the mid-ocean ridges. Deep sea trenches generally lie seaward and parallel to adjacent island arcs or mountain ranges of continental margins. They are closely associated with and found subduction zone. This location where a lithospheric plate bearing oceanic crust slides down into upper mantle under the force of gravity. So a bright example of transformed fault boundaries is the San Andreas Fault. The San Andreas Fault is a transformed plate boundaries accommodating horizontal relative motion. The San Andreas Fault is a continental transformed fault that extends roughly 1,200 kilometers through California. It forms the tectonic boundary between the Pacific Plate and the North American Plate. Yet, in an instant that cracked the San Andreas Fault line, as you can see in our image, could ruin lives and cripple the national economy. In the one event or one scenario produced by the US or United States Geological Survey, the searches found that a big quake along the San Andreas Fault would kill 1,800 people, injure 55,000, and wreak $200 million in damage.